Jack Jackson. In this video, we're going to talk about how we can generalize the product rule. It actually generalizes very nicely. Let's just focus on this line right here. Look what happens if we try to do the product of three things. It turns out if you have three factors multiplied together and you want to find the derivative, you just take the derivative of the first one times the other two, plus the derivative of the second one times the other two, plus the derivative of the third one times the other two. And this generalizes here. Here, if I've got n factors, it's the derivative of the first one times all the rest, plus the derivative of the second times all the rest, plus the derivative of the third times all the rest, until you get to the last one here. This is some notation for that. This is product notation, kind of like summation notation. This says if we have the product of k functions and we want to take the derivative, what we get is a sum from k equals 1 to n, so we get n terms. And each one has one derivative, the derivative of the kth one, and the product of all the others where j and k are not the same. So this is a little bit more complicated, very compact and precise way of saying it, but a little bit more confusing looking perhaps than just doing this. But I think you can see what's happening here with 3, and you see that works out no matter what. So I'm going to do the proof when there are 3 factors. So the way you do the proof when there are three factors is we start by grouping 2 of them, say f and g, and now we just have 2 factors. So we can apply the 2-factor product rule that we proved earlier. It's the first times the derivative of the second plus the second times the derivative of the first. Now the derivative of p is p prime, of course. Now the derivative of the second here, we can use the 2-factor product rule again. So that's f times g prime plus g times f prime, and then distribute the p. And just to get it to be a little bit more easy form, I just reordered the things here and got it as f prime times g times p. That's the last one here. And then f g prime p, that's the middle one here. And f g p prime, which is the first one here. So again, there's many orders we can write this, but that works out. So if there's 4 factors, similarly, we could break it into 2, separate one from the rest, apply the product rule, and then the product rule for 3 factors, and work our way up. Formally, we can prove this in general by induction on the number of factors. The result's completely trivial for n equals 1 factor, and the product of 2 factors we have already proved. The derivative of f1 of x times f2 of x is f1 prime of x times f2 plus f1 times f2 prime. That's a little bit different order than I usually write it, but it's the same thing. And we assume that theorem holds for n factors, and we want to consider the derivative of a product of n plus 1 factors. So this is all writing this out. I'm not going to spend a lot of time on this, but you take the product of n minus 1 factors, break it into product of n as one thing times the n plus 1, use the product rule, says it's the derivative of this product times this last one. And this says you take the whole thing times the derivative of here. This derivative is just f sub n plus 1 prime times the product of the rest. This is applying our rule. That's the sum from k equals 1 to n of this here times this here, which makes this product go up by 1. And you put all that together, it's exactly what we expect to be. So let's see if we can put that into work. So here's something with a product of 3 factors. And one way to do this, maybe not the easiest way to do this, but one way to do this is to think of this as 3 factors and do the product rule with 3 factors. Okay, and so what happens here is it's the derivative of the first times the other 2 plus the derivative of the second times the other 2 plus the derivative of the third times the other 2. Alright, the derivative of e to the x is e to the x, the derivative of x squared plus 3 is 2x, and the derivative of this one using the chain rule, this is u to the second, where u is 2x plus 3, so that's going to be 2u times the derivative of the u. The derivative of the u is 2. Now it's just a matter of cleaning up. Let's see, we've got that. I didn't make any changes there. Here I did this is just rewrote the 2x in the front. Here I wrote the 2 times 2 is 4 in the front there. Now if you look, they all have an e to the x and a 2x plus 3. So if we factor that out using the distributive property or common factor factoring, that's gone. One of those is gone, so that leaves x squared plus 3 times 2x plus 3 here, plus, let's see, that's gone. One of those is gone. That leaves 2x times 2x plus 3, plus, and then the e to the x there and the 2x plus 3, that leaves the 4 and the x squared plus 3 there. Now, I'm going to do FOIL here. X squared times 2x is 2x cubed. X squared times 3 is 3x squared. Then we got a 6x, and then we got a 9. Here we got a 4x squared plus 6x using distributive property. Using distributive property here, we get 4x squared plus 12. Combine like terms, we get 2x cubed plus x squared. So we got 3 plus 4 is 7. And 4 more is 11 x squares. 6x's plus 6x's is 12x's. And then 9 plus 12 is 21. And so we see that at least partially factored out. This may be able to be factored a little bit more depending on what we allow for coefficients. But there we can see that worked out. Now you could also do this if you wanted to. I'm not sure if it would be better. Probably not. You could probably square this out and multiply this out, but then you'd have to use the product rule at least once. But then you'd maybe want to factor at the end. I think this is going to be a little bit better than trying to go that route. All right, here's one for you to try. It's very similar to the last one. Work it out, press pause, work it out, and then come back when you're ready. Press pause now. All right, here's the solution. This is getting a little long after there are 3 factors here. But it's the derivative of the first factor times the other 2, plus the derivative of the second factor times the other 2, plus the derivative of the third factor times the other 2. So that's really all there is to the product rule right there. The rest is a couple of three pretty easy derivatives, and then a lot of algebra. So the derivative of e to the 2x is 2e to the 2x. Now there I'm actually using a substitution and the chain rule, where u is 2x, so the derivative of e to the u is e to the u times the derivative of the u. The derivative of 2x is 2. That are still down. That's coming down. That's coming down. Derivative of this is right here, so that's 5x to the 4th. And the first 2 terms are the same. First 2 factors are the same here. And then here I'm doing a substitution, say v equals 5x plus 2 to the second. So this is 2v times the derivative of v. The derivative of 5x plus 2 is 5. So 5 times 2 is 10, so I just move that to the front, put the 5x to the 4th in the front of this one, and left the rest alone. Now I'm going to factor out, if you notice there's an e to the 2x in that one, and that one as a factor, so I brought that out. And they all have at least a 5x plus 2 to the first power. So I'm going to factor that out. Let's see what happens. This still, what's left? The 2's left, that's canceled. That's still there, and you got one of these. So that's the first term inside the parentheses, plus. That's still there. This is gone, and one of those is gone, so we got this here, plus. We still got the 10. That guy's gone. This one's gone, so we got this here. All right, so as far as actually finding the derivative, we actually have it from this second line on. The rest is mostly just, well, it's completely just some algebra to clean up. But it's good to practice a little algebra. Here we're going to do FOIL right here. 5x to the 5th times 5x is 5x to the 6th. X to the 5th times 2 is 2x to the 5th. We got 3 times 5x is 15x, and 3 times 2 is 6. The rest I just copied. Now we're going to use the distributive property. 2 times 5x to the 6 is 10x to the 6. 2 times 2 is 4 for the x to the 5th coefficient. 15 times 2 gives us 30 for the x there. And 6 times 2 is 12 there. 5 times 5 is 25. X to the 4 times x is x to the 5th. 5x to the 4 times 2 is 10x to the 4th. This is 10x to the 5th plus 30. Combine like terms, we got an 10x to the 6th. 10x to the fifth, and 25 more is 35, plus 4 more is 39x to the fifth. We got a 10x to the fourth. We got a 30x, and then we got a 12 plus 30 is 42. And so there, of course, these were just kind of coming along for the ride there. So now we have it at least partially factored form. We don't know about this 6-degree polynomial. It might factor a little bit more nicely or not. But anyway, we have at least partially factored out and cleaned up at least a little bit. All right, so things, so we start with some easier examples, and then we get to some harder ones. We could do something with a product of 4, 5, or 6 factors, but the problems are going to start getting long, but still fairly straightforward. And so that's some applications, a little bit harder ones, of the generalized version of the product rule.